Okay, welcome back, guys. Sorry for the little bit of a late start. I had a little bit of a technical problem here, but it's all taken care of. Okay, we were on chapter 8 and pretty much halfway through the semester. So anyway, what I plan to do is finish up chapter 8. Then we're going to jump into chapter 9 and then finish 9 on Thursday. And I'll get you ready for next Tuesday, which is the next exam. Okay. Any questions? All right. Well, let me continue with where we left off. This chapter called nomenclature is dealing with naming compounds, but we're actually learning also how to put them together. With respect to ionic compounds, okay? And the main takeaway here is that when we're working with ionic compounds and we're given the name or the elements that we need to make a compound from, we need to first convert those into ions. And once we convert them into ions, then we can put them together properly with the correct number of cations and anions, such that they add up to 0 with respect to the overall charge of the compound. So in this scenario, they're asking you to give me a list of a variety of combinations. They give you maybe the formula. Once you give you the name, they give you the elements. They want you to create the formula. So in this case, the first one is SR, which is strontium, which is element number 38, okay, number 38, which belongs in group 2A, which is a metal. And being a metal, we know that it will have a positive 2 charge as an ion. So we need to convert that element into its respective ionic form. We're given the partner here, which is the OH, which plus a negative charge. So that in itself should tell you, oh, I'm dealing with the polyatomic ions. Okay, so become well familiar with the polyatomic ion table, which is in the far bottom left of the periodic table. Okay, bottom far left. Most of them you can see are anions. Now, a lot of times students mistake these ions for specifically covalent compounds, okay? For example, let's take the NO2, which one right here, negative, okay? Totally different NO2 negative, which has the name nitrite, okay? Which is totally different from the covalent compound, which is NO2, which is nitrogen dioxide, okay? So the fact that you've got a superscript negative charge tells you I'm working with ions and not the covalent compound, okay? So here we're using the hydroxide. So we know that this is a +2. This is a -1, the hydroxide, which tells us that we need 2 of the hydroxide polyatomic ions to cancel out the +2 of the strontium. Now, since we need 2 of them, that tells you that you're going to need a parentheses to encompass the OH negative and the subscript 2. That tells you that is the correct way to write the hydroxide where you need more than 1, okay? We don't do this, SR, thinking that you need 2 of them. You either put a 2 under the oxygen and 2 on the hydrogen. That, I have no idea what that is. It's definitely not hydroxide, okay? So you got to put parentheses around the whole unit. So that is the formula. All right, the second one, they just want the name, okay? And so we look at AU, that tells us that AU is gold, so we can write that down. Gold is not part of the 16. Remember the 16 elements that we have an exact oxidation number, group 1, group 2, and then the 4. okay? I'll show you the periodic table here in a second. So let me show you now, just to make sure that we are on the same page. Goes this. All right. So the ones I've circled in red, group 1, group 2 elements, an exact oxidation number. Group 1 has a +1, group 2 a +2. Then on top of that, those other 4 elements written in, circled in red: the aluminum, the zinc, the silver, the cadmium, with their respective charge. Okay, those are the sweet 16, as I call them. They have exact oxidation number. Therefore, they do not require Roman numerals to describe them. Okay, because we know what they are. They're always that charge. All the other metals, the irons, the copper, the nickel, the chrome, everything else requires Roman numerals to tell us what oxidation state the metal's in. So here we're given the formula, so we don't know what the oxidation state is of gold, but we do know it's not part of the 16, so we're going to use Roman numerals. So we got gold, parentheses, and then the Cls are the chlorides. Okay, so we got the base name for this. Now we're going to calculate what the oxidation number is for the gold. How are we going to do that? Well, we look at chloride. Chloride has always a -1, and there's 3 of them. That means we got a total of -3 charges, oxidation numbers for the 3 chlorides. That infers that gold has to be a +3, okay, to cancel out the -3 of the 3 chlorides. Therefore, its name is gold, parentheses, Roman numeral 3, and parentheses, chloride. Okay. Zinc is one of the 16, and that is a plus, has an oxidation state of +2. Oxygen, which is now oxide, has a -2. It's a group 6 element, non-metal. It will gain 2 electrons to obtain that octet around it. Okay, so now it's a simple 1-to-1 because I just need 1 zinc +2 and 1 oxide -2. Its formula is simply Zn, excuse me, O. All right, this one a little bit more challenging, but break it down to the ions. We're given 1 ion here, the phosphate, okay, with a -3. We know that barium is in group 2, so in that ionic form, barium will always have a +2, okay? Now we have a dissimilar charge to put together. We got a +2 and a -3. As I talked about earlier, when you had that situation, you find a common number. And the common number here, which a lot of times is going to be 6, but you can have different combinations. Most of the time, it's something like this scenario. 6 is the common number, which means that I need 3 bariums for every 2 phosphates, okay? Because the 3 bariums gives me a total of +6, and the 2 phosphates give me a total of -6. So those numbers I put in here become the subscript for those particular ions. So barium 3, and then in parentheses, the phosphate, because we need 2 of them. So that is the formula for the barium and the phosphate combination. All right, now we have this SO3, which at first sight, you might think sulfate. But keep in mind, the 2 examples we have for you are the sulfate, ATE, and then the one with minus an oxygen is the ITE, the sulfite. This is the sulfite example, okay? Lithium always has a plus. Erase some of this junk here. Lithium always has a +1, is a group 1 element, okay? Always with a +1. And that means that we need 2 lithiums for every sulfite. So its formula becomes Li2SO3, lithium sulfite. Okay. Here we have sulfur all by itself. Unlike the previous one we just did, we have sulfur bonded to oxygen, which would tell you, oh, I'm dealing either with sulfate or sulfite. Okay. In this scenario, it's just oxygen all by itself. So that is, we are dealing with the sulfide IDE. Okay. It is in group 6, which tells you that it will have a -2 charge. It's a nonmetal, it will pick up 2 electrons. So in ionic form, the sulfur becomes sulfide with a -2 charge. Aluminum is one of the sweet 16. It's in group 3, it's a metal. It will lose those 3 valence electrons. So here we have another dissimilarity with respect to charge. Find a common number, which again is 6. So we have 2 aluminums needed and 3 sulfides. So our formula becomes Al subscript 2, then sulfide subscript 3. Okay. And that would be the formula. It would be incorrect with respect to writing the correct formula to write it as Al, and then a 2, and then the sulfur, and then the 3. I have no idea what that is, but that is not the correct formula for aluminum sulfide. It's got to be the subscript. Remember, the subscript tells us how many of those atoms we need. The superscript tells us their respective oxidation number. Okay. All right, now we got another metal, copper, which is not part of the 16. So that tells you that we're going to need parentheses. Okay, but we need to figure out which parentheses. And the NO3, again, it's in parentheses here, so that should flag you to go to the polyatomic ion table and look for NO3, which you should find, which is a nitrate ion, specifically has a -1. Okay, there's 2 of them. So we've got a total of -2 for both of the nitrates, which infers, well, this is nitrate, which infers automatically that the copper here must be in the +2 state to balance off the -2 brought to you by each -1 of the nitrates. Okay, so that means that we use the Roman numeral 2 in naming copper, parentheses, Roman numeral 2 and parentheses. Don't forget the parentheses, and don't forget that the Roman numerals are in capital letters and not the small ones. Okay. Well, let me clear up my mess here and I'll put a little bit cleaner answers there. Okay, so there you go. There are the formula and the name. Okay, formula and the name for these species. Now, also remember that you can mix and match. Now, you can take the strontium and create strontium chloride, strontium oxide, strontium phosphate, strontium sulfite, strontium sulfide, strontium nitrate, and do the same with the gold. Okay, the gold, you can take the gold and hook it up with the hydroxide, gold hydroxide, whichever, in this case we may call it the gold 3, since we're using gold 3, and then gold oxide, gold phosphide, gold sulfite, etc., etc. So you can mix and match, so you're building up your database of the compounds that we are you can potentially put together. And that just not even near all the metals that are out there. We have all the other metals that we can utilize to make these respective compounds. Okay. Here in this case, we're asked to give the formula. Okay, so we're given the name. Now we're going to give the formula. Well, when we're given the name, we need to convert. And second of all, they're given a name, so we're going to write the formula. And so point number 1 is this. You can notice that they're metal, non-metal combinations, which means they are ionic. Okay. So we're going to break them first into the ions. Sodium, as we hopefully well know now, is a +1. Okay. And nitrite not to be confused with nitride, IDE, but nitride, ITE, should send you to the polyatomic ion table. And you'll find that that is the NO2 -1, okay? And so we can very quickly put them together as a 1-to-1 because it's +1 and -1. So its formula will be NaNO2, the nitride. The nitrate, if we were going to do that, if this was nitrate, excuse me, okay, then there would be sodium and O3. Notice the difference. The nitrate has 3 oxygens, the nitrite has 2 oxygens. 2 totally different compounds. Nickel 3 tells us we are using the Ni+3. The oxide is a -2, okay? And the oxide with respect to the name is going to be the same whether we're dealing with ionic compounds or here in a bit with covalent compounds. The name remains the same in either type of compound. So here oxide has a -2. We have the similar charges again. So we find a common number, which in this case, again, is 6. So we need 2 nickels and 3 oxides. So we have the formula Ni2O subscript 3, nickel 3 oxide. Okay. We got magnesium iodide. Magnesium's in group 2. So it has a +2 oxidation state when it becomes ionic. Iodide is in group 7, so it would have a -1 always. That means we need 2 iodides for every magnesium ion. So its formula is Mgi2. Then we have aluminum, which is a +3 ion. And then the cyanides, you send you to the polyatomic ion table. We also did this as a Lewis dot structure. And so it has a -1 charge. And that means we need 3 of them, 3 cyanides for every aluminum ion. So the formula becomes Al parentheses CN and parentheses 3, aluminum cyanide, okay? The breakup again is you're given the name, break it down to their respective ion in ionic form, and then put them together with the proper ratio, okay? And that is the formula. The other thing too is, again, sodium oxide, sodium iodide, sodium cyanide, as you can do with nickel nitrate, nickel iodide, nickel cyanide, magnesium nitrate, and magnesium oxide, magnesium cyanide, and the same with aluminum. Aluminum nitrate, nitrate, either one, aluminum oxide, aluminum iodide, aluminum, and so forth, okay? Again, building your metal and your non-metal combination to write actual compounds. Okay. Now, the takeaway with ionic compounds is this. If you're writing the formula, put them in ionic form first to make sure that you have, first of all, to have the correct oxidation, so that when you put them together, you put them together with the such numbers that the positives cancel out the negatives, okay? Now, with naming the compounds, if you're using any of the 16, then they do not require Roman numerals, okay? Just whatever metal name that is, that's what it is, okay? If it's anything other than that, then you use Roman numerals like we did here, nickel 3, to differentiate the different nickels that are available out there, okay? And then finally, with polyatomic ions, if you need more than one, use parentheses with a subscript to designate how many of those you need, okay? If you only need one, then you don't need a parenthesis, okay? Just like that. All right. With that, that brings us into covalent compounds and how we're going to name these. Now, and remember that these are non-metal combinations, okay? Now, With ionic compounds, I want you to keep this in mind because it's related to the chapter that we're going to be doing next. With ionic compounds, when we place them in water, when these ionic compounds, and I'm just going to do it generic, because we know that the ionic compounds are made up of positive and negative ions. When we dump them in water, they are going to break up into the respective ion, positive ions and negative. I'm just going to do it this way. POS ions to represent the positive plus, NEG to represent the negative. So they're going to break up. They're going to dissociate. Okay. Now, a lot of these ionic compounds will dissociate into the respective ions 100%, but there are some that will dissociate much less than 100%, 5 to 10%. Nevertheless, they will remain intact, but they will have a little bit of ions in solution. The point being is this: with ionic compounds, they are all conductors of electricity when you put them in the water solution. Some of them will be a very strong conductor of electricity. Some will be a weak conductor of electricity. And that is related to their solubility in water. And how we're going to determine that is we're going to go back, guess what? To the periodic table. And so be familiar with this table on the bottom right-hand side, which deals with the solubility rules, okay? And these rules, they look complicated here, but really it's very straightforward. We got two columns. The column on the left are what are called the solubility. Any combination that we're going to talk about, they are soluble in water and basically dissociate 100%. The other ones on the right column are classified as insoluble. Those guys, normally the majority of them stay intact. There are some ions in solution. In both cases, they will conduct electricity because they're making ions. So if you have pure water and you check the conductivity of pure 100% water, it would not conduct electricity because water is a covalent compound. It's not broken up into the respective ions. The moment I throw in one of these ionic compounds in that water, it becomes a conductor of electricity. Some of them are strong conductors, some of them are weak conductors. And that's related to the solubility rules that we're going to eventually become quite familiar with. Okay. All right. Now, with respect, and that's about the ionic compounds. With respect to covalent compounds, with the only exception of what we call acids, they do not dissociate. They remain intact. As I stated, water does not dissociate. Okay, it does not conduct electricity because there's no ions in solution. Ions are very important in our body. The conduction of electricity from the top of our head to the bottom of our toes occurs because there are ionic compounds in our body that allow the signal, the electrical signal to be moved from point A to point B. Okay, so we know about this obviously by now, right? That we are dealing with nonmetals, and these are not ions. They do have partial charges, okay, only because of the dipole involved in the bond, but still they're not conductors of electricity, even though they do have partial charges. Now, in the case of the ionic compounds, we did not use prefixes at all. Okay. For example, the last one is called aluminum cyanide. It is not called aluminum tricyanide, nor is it number 2. It's not called dinickel trioxide. Not at all. Ionic compounds do not use prefixes. Okay. Put that in long-term memory. Covalent compounds do. We use prefixes. And the prefixes we mainly use are given here. Mono represents 1, di represents 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8. We also, you may see occasionally for 9 called nana and nona. And N-O-N-A, and that's for 9. And then deca, E-E-C-A, for 10. Okay? Those are prefixes that we utilize. So be familiar with the prefixes because we'll be utilizing. Okay, now the manner in which we name them is as follows. Written in green is a prefix which may or may not be there. Okay, plus the non-metal name. Okay, followed by a prefix for the second. First is the first non-metal name, and then the second non-metal name that has been converted to the IDE ending. Okay, IDE ending. Now, if the first you're always going to have it in this setup. You know you have an ionic compound because you're going to see it written with the metal first, followed by the non-metal. Automatically, you have that's by convention. That's the format: metal, then the non-metal. With respect to covalent compounds, you're going to have no metal in there at all whatsoever. But the first element that's written, you can treat that as the central atom. And then what follows, whatever non-metal follows, is bonded around that central atom. Most of the time, that first element is 1, okay? It's a single element. Now, and that's the case, you don't have to use the prefix, say monocarbon dioxide. It's understood there's 1 carbon dioxide, okay? The second element bonded to the central atom, yes, you're going to use prefixes, be it mono all the way up to whatever number you're going to put in there. And so hence you have the example, and we'll do some examples here. Okay, is this one. We call this carbon. Okay, there's 1 element. We don't use monocarbon, we just call it carbon. And then oxide. It's the same oxide that we use for inorganic compounds. But then we add the prefix di because it represents 2 oxygens compared to this one where you have carbon, same as the previous example, but now there's only 1 oxygen. Hence, we introduce monoxide. 2 different species, carbon dioxide and carbon monoxide. Okay, 2 totally different species, different properties, the whole thing, different compounds. Okay, here we have a phosphorus and then followed by oxygen. So phosphorus is the central atom. So we write, we're given the formula, we need to write the name. So we write what I call the base name. Okay, phosphorus and oxide. Okay, we don't call them, oxygen is going to be called oxide, whether it's bonded with the ion as an ionic compound or whether it's bonded as a covalent compound. Okay, so the parent name is phosphorus and oxide. Then we go look at the prefixes. There's 2 phosphorus, so we add di for the 2 phosphorus, and then there's pentoxide, P-E-N-T-A. Okay, so we have phosphorus, pentoxide. So we wrote the parent name, then we wrote the prefixes. Now, with respect to English format, by English rules, you have a vowel here from the prefix penta, and then it's going to be attached to another vowel. Technically, we're supposed to drop that A. Okay. So pentoxide. Now, whether you drop it or not, I'm not too concerned. Okay, because my issue with this, if you look at the example of dioxide, okay, if it's a vowel I and there's always another vowel, technically you're supposed to drop the I, right? So it'd be doxide, but we call it dioxide. So point being, if you don't forget to drop the A, not a problem. I'm not going to take take any points at all. So with or without the prefix or the letter of the prefix is fine. All right. Second one. Again, we got phosphorus in the written first, so that is definitely the central atom. In the previous example, there's two phosphorus, so basically it's a big old complex. There's two phosphorus in the middle, and then oxygens are bonded around that two setup. Here we only have one phosphorus, and then we have the fluoride. It's not fluorine, whether it's bonded with an ionic compound or a covalent compound, it still is called fluoride. And then we got three of them, trifluoride. So it's called phosphorus trifluoride. Okay. Then we have this one. Now, you might think it's a strange looking species, but it's just to show you that some of the halogens, the bigger ones like bromine, iodine, and so forth, they can act as a central atom. Normally, we think of them as just being the ones attached to a central atom, but they can also be be put in systems where they are the central atom. That being the case, the name is iodine, not iodide. It is the name of the element because that is a central atom. If it was followed by iodine, then we would change that name, let me restate that. If it was, I don't know, let's make one up, sulfur and three of these or two of these. If there was Si2, then that would be called sulfur diiodide because the iodide are bonded to the central atom. Okay. All right. So in this scenario, it's the iodine central atom, and then we got the fluorides. And then we do the prefixes, which would be hepta. Okay. So it's so that's the name, iodine heptafluoride. Right. Now, another I'll give some more examples how to distinguish between calling it sulfide, calling it sulfur. We'll do some more examples here in a second. And as a general guideline here, when you see the formula, you'll see the first element, whatever it may be, that will represent the central atom, and then whatever follows will be is bonded to the central atom, and we would change those to the IDEN. Okay. All right. So in this scenario, it says, given the formula, write the name and vice versa. So here we go. Here we got bromine. Okay. Notice it's BR written first. That tells you that the base name is a bromine. If it was written second, element-wise, then it would be bromide. Okay. So here, base name is bromine. And then we got the oxygens, which again are oxide. Okay, so there's the base name, bromine oxide. Now we use the prefixes. We got three bromines, so that's tri. And then we got octoxide for the 8 oxygens. Okay. All right. Now we have base name. We got phosphorus like we did before. Phosphorus is written first. And then followed is sulfur, which because it's bonded to the central group of 4 elements, it is sulfide. Okay, so that's our base name. And then we add in the prefix, we got 4. So it's tetra phosphorus and then heptasulfide. Okay. Its name is tetraphosphorus heptasulfide. Okay. Notice the difference if it was, let's say it was this species, sulfur, which I think is the next one. So in this scenario, we got SO3. Sulfur is written first, so its name is sulfur, not sulfide. And then we follow by the trioxide. Okay, so notice the difference here. When sulfur either is bonded to the central atom or when sulfur is the central atom. Okay, and that would be true for any element that acts as the central atom. Its name is whatever its name is in the form of an element. All right, like that one, sulfur trioxide. Okay. And then you also have SO2, which is sulfur dioxide. And now you're given the name and you want to figure out the formula. So as we did with working out the name by giving the base name in this scenario, write the base formula and then throw in the prefixes. Okay, so here we have sulfur and fluoride. Excuse me, iodine and fluoride. So we got an I and an F combination. Okay, there's only one iodine, but there are 6 fluorides. So its formula would be IF6. In this scenario, base name, notice here, it's chlorine. Chlorine is the central atom. And then pentoxide and oxygen. So we got Cl and then oxide. Okay. We got 2 for the chlorine and 5 for the oxide. So base name, then come back with the prefixes. You know, and again, I always advocate a systematic approach. And then as you get comfortable, obviously, you can bypass all that and go directly to the formula. Okay. And then here we're given the formula. I want to get to the name. So base name, phosphorus. First, and then followed by iodide. Okay, now we do the prefixes. We got di for 2 phosphorus and tetra for the iodide. Okay, so its name would be tetraiodide, diphosphorus tetraiodide. Some of these could be a little bit of a tongue twister. So, all right. So a few reminders. 1, prefixes only for covalent compounds. Okay. Roman numerals only for those elements, those metals, I should say, that have a variable oxidation number. Okay. Polyatomic ions, they have their own specific name. We don't change the name. So a nitrate is a nitrate, nitrite is a nitrite, etc. Okay. And then with that, tell you what, you got 3 minutes, knock it out. What do you think? First one, BaCl. What could I call that? Well, barium, obviously, right? And then the Cl is the chloride. Okay, notice no prefixes, no Roman numerals, no Roman numerals, fine. Barium is part of the 16, okay? And then chloride, no prefixes as dichloride, it's just chloride because it's an ionic compound. Okay. Here, nitrogen and NO2. Notice there's no charge up there. Okay, this would be the polyatomic ion, nitrite. There's no charge here, so this is the covalent compound. So we have nitrogen dioxide. Nitrogen dioxide. Okay, now we have this one here, and I showed you a little technique you can use to quickly just by looking at the subscripts of the anion and cation to determine which oxidation number you are working with respect to the metal. But let's break it down. Okay, we'll do it the long way. We have PO4 in parentheses. The parentheses right there should tell you, oh, okay, we are dealing with PO4. I go to the periodic table, polyatomic ion table, and that is phosphate as a -2 charge. Okay, and we have two of them. All right, now we have 3 irons. And we don't know what the charge is, but we do know there's 3 because iron is a variable oxidation. So we need to figure out which one it is. So we set up a little simple algebraic equation. We have 3 irons. Okay. We know this whole thing is going to be equal to 0. Okay. We just learned that the phosphate each have a -3, and there's 2 of them. So that means there's a total of -6 for the phosphates. Okay, so here's our algebraic equation. Now we got to solve for iron. So it's 3Fe, add +6 to both sides, and now we can divide through by 3. Okay, so Fe is equal to a +2. So that is the oxidation state of this iron. So the name is the parent name, iron, parentheses, Roman numeral 2, phosphate. Okay, and this is the method we utilize to figure out the oxidation state because we know that the overall charge is 0. That was one way to do it, right? The other way was if you look at the subscript of the anion, that turns out to be the oxidation state of the cation, right? We just calculated that. Okay. And if you look, I just lost connection, I'm thinking. All right, you still here? All right, yeah, you're still here. I lost connection for a brief second, so we'll see what happens. This happened earlier. All right, so as I was stating that the oxidation state of the subscript of the anion happens to be the oxidation state of the metal, and the subscript of the cation happens to be the oxidation state of the anion. Okay, so very quickly that tells you that you're using iron 2 phosphate. Okay, one way to look at it. Bear with me a second. Okay, it looks like I'm having some kind of a issue on my end. Bear with me for 1 second, please. All right, so we did that one, and then we have so this was iron 2 phosphate. Okay. And then we have diiodine tetroxide. So we do the base formula first. So we got iodine and oxide, then the prefixes. And so we got I2O4. Okay. Silver is the symbol Ag is part of the 16. We know that it has a plus 1 charge. So Sulfate 8 tells you go to the polyatomic ion table and you will find this formula. And so that means that we need 2 silvers for every sulfate. So that's his formula. Okay. Nickel 3 tells you that we are dealing with +3 ion. Sulfide, IDE, tells you we're dealing just with the sulfur by itself. Remember I said the IDE is normally just the element itself. And plus it's got a -2 charge because we're dealing with ionic compound here. And so we got a dissimilar charge, so we need 2 nickels and 3 sulfides. So our formula becomes Ni2S3. Here, let me clear up my mess. Get you a better picture. Okay, there you go. All right, so, and again, you can mix and match here, barium with the oxide, barium with the phosphides, barium with the sulfate, etc., barium with the sulfide, so on and so forth. Okay, so your database of compounds should be building up pretty good. There is a worksheet on chapter 8. Don't forget to do that. It will help you with this. Also, don't forget StudyMate. I put a link on the left panel called StudyMate. About 140 compounds were uploaded that you can do like a flip chart to help you. You're given the formula. You can write the name and vice versa to help you out. Okay, that being the case, congratulations. We are done with chapter 8, literally half there. All right. Any questions? Any questions? All right. Well, that being the case, then what we're going to do is continue with chapter 7, where we're going to talk about acids and bases and why I lost my. Were you guys able to see my shared screen? It just somehow my video stopped. Yes, okay, thank you. All right, that's good. All right, so with respect to acids and bases, okay. Now, there are 2 definitions of an acid and a base. I'm gonna talk about that here in detail. Something's happening again. There we go. Okay, don't know what's up. Good old Zoom. All right, acids and bases. Now let me stop first and talk about an acid first, and let's briefly talk about hydrogen. Now you may have noticed that hydrogen is in the upper left first row, 1A row, along with the metals. And it's there because hydrogen is has 1 electron, just like everybody else in group 1. So they share that property and share a lot of the general type of chemistry, actually, share that property. And also remember that when we talked about the electron configuration, that 1 electron was in the 1s1. That was the electron configuration for hydrogen, the very first one, the first energy level, the s orbit 1. Now, that means, if you recall, that the s orbitals can handle 2 electrons. So It is feasible. It is feasible. This is hydrogen, elemental hydrogen. That hydrogen can gain an electron because it has room for it in that s orbital, resulting in a Lewis dot structure like so with two electrons. But overall, like the halogens in group 7, where they gain one electron, they end up with a -1. And that has a special name called hydride. Okay, just like chlorine becomes chloride, so on and so forth. I mean, sometimes you might find hydrogen also placed not only in group 1, but it's underneath group 7, because they can pick up one electron like all the other halogens to give you -1. Okay, but we're not going to talk a lot about the hydride. Like, and as I stated, the reason it's in group 1 is because it shares the same type of chemistry. Now, what can happen is that one electron of hydrogen can be lost, lose it like the metals underneath it, resulting in what we call a proton. Okay, proton, and it has a positive charge. And so that 1s orbital is empty now. Okay, because there's no electrons there. All it has is a proton, positive charge. Then you have a neutron for this isomer, right? And that is what defines what an acid is anything that in put in solution, and we're talking about going into solution, into aqueous solutions, that generates or creates a proton is classified as an acid, okay? Classic example right now was what's roaming around in your stomach. You have an acid in there specific called hydrochloric acid, HCl. Okay, that is if you have an acid reflux problem, that's what gives you the acidity and the heartburn and the pain and so forth. All right, so that's what we're talking about. But keep in mind the fact that that orbital is empty. That orbital is still there, but it's empty. And that's going to be important here in a second when we describe that electrons can be put into that orbital and shared, okay? Any orbital that's empty, that's still there, can have electrons inserted in the area, and you can share electrons with the other species. Okay, so an acid. It is anything that produces a proton, which is nothing more than a hydrogen atom that has lost its electron. Okay, at 1s1 electron is gone. In general, and you're well aware of this, you drink vinegar. Vinegar is an acid. That's an organic acid, and a lot of other vinegar, anything sour. Okay, has citric acid. Another example of something that's sour tasting. It can be very corrosive as far as reactivity. And we have a real simple test using what's called litmus paper test. And all that tells you whether something's an acid or a base. And specifically blue litmus paper, if you take blue litmus paper and put in a solution of an acid, it would change it to red color, okay? I'm sure if you have a swimming pool at home or done that, or check an aquarium one, check the pH. You have pH papers that give you the spectrum of the pH scale. But litmus paper, just yes or no. It's an acid if it turns blue from blue to red. Now, with respect, thing about acids is this: covalent compounds produce acids. Okay. Covalent compounds. HCl is a covalent compound. Nitric acid, we're going to learn about. Sulfuric acid. All of those are covalent compounds. Okay. Now, anything that produces that polyatomic ion OH, which is the hydroxide. Okay, this is that hydroxide ion. Anything that produces that is classified as a base. So what that means is this, that the bases that are made that we're going to work with are all ionic compounds. Okay. Like sodium hydroxide, any metal hydroxide combination is a base. Some of them are very strong bases because they dissociate 100%. And some of them are weak bases because of the solubility rules. They don't dissociate as much, okay? But nevertheless, they're still bases. If you were to taste them, which I wouldn't recommend, they are bitter and they kind of look chalky, okay? And they feel soapy and slippery. The reason they feel slippery and soapy is this. If you ever had any liquid plumber at home, because you got a plugged up drain, liquid plumber is good because it dissolves greases and so forth. And what it also does, if you get some on your hand, it feels slimy. It's not necessarily chemical that's causing the problem. It is that bases tend to denature and break down the tissue of your skin. In fact, a lot of facial treatments are alkaline in nature. The idea being to strip away and dilute and get rid of some old tissue. Okay. All right. They will take red litmus paper and convert it blue if it's a base. Okay. Now, there's two definitions. The first one is called the Arrhenius definition of an acid. Okay. As I stated, here's hydrochloric acid. Okay, it is a covalent compound. The nature of the base is this: it will dissociate into the respective proton and the chloride when it's in solution of water. It's dissolved in water. Okay. This is a strong acid, which means that it would completely dissociate 100%. Something like vinegar, which is also an acid, is considered a weak acid because it doesn't dissociate 100%, much less than 100%, much less, but it still dissociates nevertheless. The bulk of that remains intact. Okay. Now, anything that produces a base, a hydroxide ion is a base. Hence, sodium hydroxide is a good example. All right. Now, sodium hydroxide, when you put in water, first of all, it gets very warm. You got to be careful. It's very hot, and it dissociates into the ion and sodium ion and the hydroxide ion. Okay. Some of them dissociate, like I said, 100%, meaning there's a lot of ions in solution compared to others that are not as soluble but are weak as far as the strength is concerned. When we talk about strong acid, strong base, we're simply talking about the degree of dissociation and the degree of solubility. Okay. Now that is the Arrhenius definition. Anything that produces a proton is classified as an acid. Anything that produces a hydroxide in aqueous solutions is classified as a base. Okay. Now we're going to introduce you to the first type of chemical reaction, and that is simply between an acid and a base. When you react an acid and a base, you get two products only. One is water, because you are in effect neutralizing the acid and the base, and the product of that is water. Okay. Think of it next time you eat some Tums or some Mela. Your stomach is, not feeling very well, feeling a little sour, a little acidic, so forth. What do? You ingest some Tums or some Maalox, and what that does is that reacts with the acid in your stomach, neutralizes that excess acid to generate water and a salt. Now, not necessarily when you think of salt. Now remember this. When you think of salt, don't just think of sodium chloride, which you put in French. Think of it's an ionic compound. Okay. So now here's what's happened. Earlier I explained that the HCl would dissociate and produce the acid, the proton, okay, which had a positive charge. but it also had that empty orbital. Remember, I explained that one electron is gone. And the hydroxide, if we do the Lewis dot structure, we end up with 3 pairs of lone pair of electrons for the hydroxide. Okay. Guess what? Got a positive and negative. They come together 1 to 1. Now, what's going to happen is that lone pair is one of those lone pairs is going to connect with the empty orbital of the hydrogen to form a bond. Okay, and hence you create water. You neutralize it. Okay. And what's happening here, you got HCl that breaks up in solution. Okay. And then you got sodium hydroxide that also breaks up in solution. And then the proton, which is the H, and the hydroxide combine to form water. Okay. And what is left is the cation of the base and the anion of the acid to form the respective salt. Okay, which is just floating out there in solution. Okay, not doing anything. You're spectators, actually. Okay, so some food for thought, because there's a lot of advocates out there about drinking alkaline water. I'm not going to be pro or con about it, but I'm just going to give you some chemistry. Okay, this is your stomach. This is your alkaline water, which means that it has a pH of 8 to 9 pH, which has a lot of hydroxide in there. This happens, you drink it, it gets neutralized in your stomach, and you end up creating water. Now, you don't want to ever change your pH of your stomach drastically. It will cause all kinds of health issues. The pH of our stomach is set for a specific reason, and mostly because of the configuration of all the different enzymes and so forth in our body, that if the pH was not as low as it is, I'm going to learn about the pH scale, we wouldn't be able to digest or break up any of the foods that we do. Okay, so anyway, think of that when you drink your alkaline water, you're neutralizing your stomach and then creating salt, all kinds of salts. And if you have an issue with high blood pressure, you really don't want to have too much of sodium in you, so as far as your salt is concerned. All right, so this is your first example of a type of chemical reaction. Point number 1 is this. I had a proton reacting with the hydroxide to give me water. 1 proton requires 1 hydroxide to give me 1 molecule of water. Okay. 1 billion protons require 1 billion hydroxides to give me 1 billion molecules of water. That is what we call a stoichiometric relationship. It's a 1-to-1. We're going to be using those type of relationships down the road when we start doing calculations. We can do a calculation, say, if I start off with 10 grams of acid, how many grams of water am I going to make? Okay, and we're going to be using the technique that we talked about when we're doing the conversion factors to be able to do these calculations. But we have to first recognize the reaction. Then we got to balance, and much more on that later on. All right. Now, the other type of a definition for an acid and a base is what is called the Brownstedt-Lowry acid-base definition. Okay. Now, the advantage of the Brownstedt-Lowry is this: that where the other definition, as far as a base is concerned, you have to be a compound that produces a hydroxide, plain and simple. And that kind of didn't work for a lot of compounds that acted as a base but had nothing to do with hydroxide. And so the new definition is as follows. They kind of share the same definition for an acid. In both cases, you are generating a proton to make an acid. Okay, so Brownstein-Lowry, they say, okay, you lose a proton. All right, so you lose it. Well, it goes in solution. Same like Arrhenius, it creates a proton. So lose, create, it's a proton. Where they differ is the base. And a Brownstein-Lowry base is any chemical that accepts that proton, basically neutralizes. And remember way back when I was talking about lone pairs on the central atom, said they are always, you can find them to be polar. One additional thing about those lone pairs on the central atom is they can act as a Brownstein-Lowry base. Remember, we did the Lewis dot structure for ammonia, NH3, and we ended up with a lone pair on the central atom, right? That lone pair. Remember, I just talked about the proton that also had an empty orbital, okay? So what's happening here, there's a combination where we can create a bond and generate, remember this polyatomic ion, the ammonium ion, where now we have the original 3 hydrogens, but then now we have an additional hydrogen that the acid brought in and the ammonia reacted with to form this complex with a positive. Remember, we had a bracket around it and we had positive outside. Okay. And so the ammonia has nothing to do with hydroxide in here, but acted as a base because it neutralized the proton by having that proton attached to the lone pair that the nitrogen had. Okay. So all right, so what we have here is kind of a diagram. It's still a model of what's going on. Okay. So the ammonia gains a proton and the hydrochloric acid, in this case, loses or generates a proton. All right, so let me do this. I'm going to stop it here. You're in the same age as my other one. You got about 5 minutes anyway. So, done 9. But you might, if you read ahead, when you look at this strong, we're going to talk about strong acids, strong bases, weak acids, weak bases. And when we speak of those, what we're talking about is the amount of proton that goes in solution. So if an acid goes 100% in solution, it's going to be a strong acid. If it doesn't go as much, then it's a weak one. That's all. The strength is a function of how many ions are in solution. A bunch or not a bunch. Okay. Basically, in a nutshell, that's what we're talking about. All right.